Hello everyone, today I'm going to be talking about transition state diagrams, or also known as reaction coordinate diagrams. I personally call it the Delta G diagram, but whatever you want to call it. So before I begin this video, I just wanted to say if you enjoy this video, please follow me here and on YouTube. I'm only going to post part of the video here on TikTok, and the full video is going to be on YouTube. Again, if you enjoy this video, please follow me because it takes time to create this content, and I want to know that you guys are fully enjoying it. Okay, so going back to the video. So in purple, it's so because I put the pink so that way you'll be able to distinguish the pink and the blue, so that you'll be able to distinguish the amount, for example, for the delta G, to make it like the division or the line easier, because sometimes it can get confusing when they put like a bunch of dotted lines everywhere, and so I just kind of wanted to make the division easier. So the reactants would be like the purple line, the products would be the orange line, and between the purple and the orange line, the line that I have in green, is the overall delta G. This is the free energy. So I just wanted to make a side note or side comment, because sometimes students get confused on like, for example, if we were talking about enthalpy, right, and delta H, we would say something, a reaction is exothermic or endothermic, right? So this is where that comes from. If you replace the delta G with a delta H, literally the reactant is here on the top, the product is here on the bottom, you're going down, it's negative, it's exothermic. But let's say the product was here at the top, so the reactant is here and the product is here, so it's going up, it's endothermic. That's why then it's positive. So for some people it doesn't click, but sometimes the professor doesn't even explain it in that way. So I just kind of wanted to give that as a side note. But now that we're talking about delta G, remember that, so the positive, instead of endothermic, it's endergonic, and the negative would be exergonic. A last side note that I wanted to say is that, so going back, the activation energy does not like influence at all like the spontaneity of a reaction. What determines if a reaction will or not occur is the delta G, and just drill that in your head. It's not the activation energy, it is the delta G, it is the overall energy. Remember, if it is positive, it's endergonic, and if it's negative, it's exergonic and spontaneous. So that is what determines the spontaneity of a reaction, is the delta G. And the activation energy is, per se, the energy between the reactants and the transition state, like the energy it takes for the reactions to get to the transition state. And I think those are the comments I wanted to make about the diagram. However, two more things. So on your y-axis is the overall energy, and on the x-axis is the reaction coordinate, hence the name reaction coordinate diagram. And the transition state, just to be a little more specific, so if you have a reaction from A to B, like obviously it's not just automatically going to be B, right? Or whatever the reaction is happening is not going to automatically become the product. So there has to be a change of electrons or a change of atoms or something going on, right, to contribute to that change, and that is going to be the transition state. It's the middle, like the in-between phase of the reaction. Okay, so going on to the bottom, what I have for you guys. So sometimes you'll see these diagrams, right, and they'll have multiple transition states as denoted here, and they'll say, okay, which one is the slow step, which one is the fast step, what is the determining step? Okay, so just get this straight. The slow step is the one that has the highest activation energy. So I tried to make it as obvious as possible. So this is the one, in this case, that has the highest activation energy. And notice that in this one, I'm not starting from here. I'm starting from here, which is the intermediate. I'm starting from here to this next curve. Just wanted to make that a point of that. And in this case, this is the slow step. Why? Again, it has the highest activation energy. And the one that has the highest activation energy, the slow step, is also known as the rate determining step or the rate limiting step. So I hope you enjoyed this video. And again, if you did enjoy it, please, please, please follow me here and on YouTube. And thanks again for watching. Like, follow, and share. Thanks again.